Okay, I'm going to videotape myself drawing this. It might be a little rough, so we may stop and kill this. But we need to get a spherical conversion factor, right? So my goal here is to find out what d volume is in spherical land. Is all good with that? Okay, so d volume I know is dx, dy, dz, right, in Cartesian. Is all good with that? Okay. I also know that it's r dr d theta dz in cylindrical land, because that's just a polar area times a change in height. Is all good with that? Okay, so let's see if we can figure out the cylindrical one. So for the cylindrical one, I need a good picture, which I'm probably not going to get today. So I've got an x, a y, and a z. And now I need to think about, there's going to be some stuff. So stuff, and then d rho, d theta, d phi, right? Is all with that? Okay, so the first thing I need is a little change in theta angle, because I know what that looks like from drawing this picture for polar, right? So I'm going to go, okay, so there's a change in theta. It's all with that? Cool. Questions, things? Good. So that's me with my little sword, right? And that's one of these. Okay. Now there's also going to be one of these guys, right? So that's going to be my change in phi. So I'm going to sketch that in here, and this is where things get weird, because that has to be over the top of those two things. You okay? Surviving? You broke it. Jeez. Wow, that's going to come out of your paycheck for sure. Wait, no, that comes out of my paycheck. Shit.
You can just blame it on the next class. They'll never know.
Totally. Good idea.
That's what we did with our couch.
Okay. So, and this is where my picture gets horrible. So that's one of these guys, right? And then I need to push that out a little bit. So I need one of those guys. And then there's another one on the back and another one on the bottom. You guys with that? Those are at a constant row, right?
Is that the combined theta and phi?
Yeah, so there's three of those. It's hard to see. Maybe I should be doing this. So one of them's like this, and there's a mirrored one of those over here, and then there's a chunk across the top and a chunk across the bottom. Oops, shit. There you go. F.
So it's like the outside of the sphere?
Yeah, so this is a little chunk of a sphere, right? This is a square on a sphere. Okay, see that? And then there's a change in radius. So there's another one of these out here. And then these are all connected. And I'm not drawing the bottom one in there. Ah, this thing looks horrible. I need a muskmelon. Is kind of with this?
Yeah.
So there's this little kite on a sphere, right? Like a little square on a sphere. And then there's another little square on a sphere. And that one's a little bigger, right? And then these are connected. This is connected. That one's dotted. What did I do? I don't know what happened to that one. Oh, I drew one too many things. That's what happened.
Yeah, to the top outside.
There's a picture on your channel.
I know, but I wanted to make my own, but then it's all disintegrated into horribleness.
So it's like a piece of
I
watermelon.
can see what it looks like.
Okay, so this is a chunk of muskmelon, right? If you have a melon and you slice a wedge of muskmelon out, honeydew melon? Cantaloupe. Pick your favorite round thing with a hole in it. Pumpkin. If you cut square eyes in a pumpkin, this is the shape you would get. You guys all see that?
You get a wave.
Okay, so let's look at our little shape here. So I think it should be totally clear that this is delta rho. Right? Like, that should be really obvious. That thing is as thick as you have said we're changing the radius. Right? You guys all see that? Okay, now things get harder. Because now we have to figure out the other sides. You guys see this? Okay, so this is the part where things get hairy. I need to add some stuff to my picture. So let's see, let me come up to here, and I'm going to add these little guys. You guys all see those? With?
Okay.
So those are connecting these top two corners
That's the x.
to the origin.
Is it the x and y distance from the z-axis to those two corners?
X and Y distance. Yeah, they're kind of the local radii, right?
We're basically proving that this is going to be theta here.
Yeah, so there's going to be a delta theta here, right? You guys all see that? Like, that's where this is coming from. There's like some kind of a change in theta here. But,
Ah, it's a different theta than the bottom one.
yeah, so the change in theta is the same as the delta theta at the bottom. You guys all see that?
Yep.
Because this picture is above that, right? So if I smashed it all down, it's still, the angle's still changing theta. But what's jacked up here? In polar, I just got a radius, right? Here, I don't just get a radius from any darn thing. You guys see that? Because the radius for that isn't a radius I know. You guys with me?
Okay,
Kind of?
somewhat.
Okay, so let's see if we can find it. We should be able to figure this out. We're smart, right?
Hard one.
Okay, so let me add a piece of information to this. This angle here, and I've very carefully drawn that so that it's not clear which thing it goes to, is which kind of thing?
Angle.
Yeah, which angle is that? Is that a theta or a phi kind of angle?
Phi is coming off of Z.
That's a phi angle, right? You guys all see that? So if that's phi, what's this thing here?
Theta.
R sin phi.
Oh.
You guys all see that?
Oh my gosh.
Because
Yeah.
this thing here, right, is rho. You guys with me?
Yeah.
So this guy's length is, and I'm really just doing this distance, right? That should be rho sine phi. You guys with me on that? Okay. So that's the radius up there. So how long is this top arc length? I'm looking for this length here.
Multiply that by delta theta.
Yeah. You guys all with that? That's rho sine phi is the radius up there times the angle, which is delta theta. So this thing here is rho sine phi delta theta long. Okay, I got two of them. I need that third one. So how about that other guy? What's the radius on that one?
so this is the phi. So
And what's the change in the angle? Or what's the angle?
well,
You guys see this guy, right?
yeah.
That's that little dude there that I'm looking at.
This is I know this is going to be a change in phi, but
That's going to be a change in phi, right?
yeah.
Okay. So there's going to be a delta phi at least. And what's the radius there?
Just row.
Yeah, that's just rho. It's not even the opposite of the other one. It's just rho. Right? Because you're actually talking about that whole radius. That's what's changing with that little angle. So that's a rho delta phi. You guys see this?
Okay.
So what's your volume of this shape?
That would be
It's approximately
rho squared sine
delta
phi.
phi.
rho squared sine phi delta theta delta phi delta rho. Which, as you crank everything to 0, turns into d volume, right? Oh, this is a change in volume. Sorry. So your little volume boxes are rho squared sine phi times d rho d theta d phi rearranged in whatever order.
So that's the conversion factor.
Yep. So the conversion factor for this one's a little worse than polar, right? You guys see that? Shit happens. It does spheres a lot better than polar does. Should we check and see if it works?
Sure.
Affirmative.
Okay. Let's check really quickly and see that it works. So, here's your example. Go to. How big is the sphere of radius r? I should be able to figure this out. If I can't find the volume of a sphere with this thing, this was not a useful technique and I should just quit and go home. Right?
It's about that. Okay.
And it's about that time anyway, so. All right, so how do you find the volume of the shape?
So
The sphere?
Yeah, what do you want to integrate?
Oh.
it's radius r. So
Yeah, except spheres and spherical seem like they go together, right? So let me integrate in spherical. So I'm going to integrate 1 with rho squared sine phi. Right? So you got your function you're integrating, 1. I'm just going to assume that this is density 1. And then I'm going to get the conversion factor. And then I need to decide on an order of integration. I don't know. Pick one.
should we start with rho? Or
It shouldn't matter, right? Because it's a sphere. It should be a rectangle, right?
and then
Saying that
let's
like it makes sense.
do, let's do rho theta phi.
But spheres expressed in spherical should be like rectangles expressed in rectangular, right? There shouldn't be any functions in your bounds, in other words.
Then let's do rho theta phi.
Okay, so let's do d rho, d theta, d phi. Sure. Okay. Where do your rhos vary from?
From 0 to r.
0 to capital R in this case. Where do your thetas vary from?
0 to 2 pi because it's a full circle.
0 to 2 pi. And where do your phis vary from?
Again.
0 to pi because it's the
0 to 0.
Oh yeah, 0 to pi.
0 to just pi. If you go to 2 pi, you'll cover this thing twice. And you'll get twice the answer you got. You guys cool with this? Okay, so now we should integrate.
Bum, bum, bum.
Okay. Please note, you can quite easily pull the
They don't rely on each other, so you just.
Oh, you could.
they don't rely on each other at all. So you can pull the double integral trick, but in triple integral land, right?
So the theta could just be kicked out and become 2 pi is what you're saying?
So this is, I'm thinking 1 times rho squared times sine phi, right? And then I'm kind of thinking to myself, well, 1's a function of theta. Rho is a function of, or rho squared is a function of rho. And sine of phi is a function of phi. So I can pull this apart into the product of the 3 things, right?
Okay.
So what are your 3 things? The integral, what's your d theta one?
Your d theta is just 2 pi at the end of it.
Okay, yeah. So it's from 0 to 2 pi of 1 d theta, right? And then you need to multiply by the integral from 0 to pi d phi. What's your, that's sine. Oh, we can use the cool trick we learned the other day, too. And this is times 0 to r of rho squared d rho. So why isn't it 0 to rho? Is that what you're asking, Priya?
Yeah.
It would be a little weird. So this thing categorically at the end, right? The volume of a sphere of radius capital R should be a function of the radius, right? That capital R. This rho is talking about the radius on the inside of the region I'm talking about, not the outside of the sphere that I'm talking about. You guys all see that? Okay. It's also a little, like, and this is one thing I actually care about in terms of form for some reason. It's a little bit screwy to write an integral depending on rows with rows in the bounds, right? Like, yeah, that's sort of bad form. It's like not drinking after you toast. It gets rude, essentially. Okay, so we got 2 pi. What was the cool thing we learned the other day about sine? You all forgot.
Area under the curve is 2.
The area under a full loop is 2. Is this a full loop?
No.
0
It's
to
half.
pi should be a full loop.
Yeah, it's a full loop.
Oh, it's a full loop. Okay. Oh, 1 loop. Okay.
Yeah, so that's a full top, right?
Yep. And then
And then this guy is,
1/3 r to the 3rd.
so you got capital R cubed over 3. Anybody ever wonder where the over 3 in the spherical, in the formula for the volume of the sphere came from?
Yeah, I
It
guess.
came from integrating rho squared. Okay, so you got 4 pi r over 3. Oops, 4 pi r cubed over 3. Which seems familiar. Do the units line up? This is a question you should ask yourself. At the end, do the units line up? Are the units the right size? What should the units on a volume of a sphere be?
Some measurement cubed. Whatever.
Yeah, whatever the radius units were cubed, right?
Yeah.
I got a cube on the radius. Check. That's a volume kind of thing. Cool. Good? Questions?
Can I make an announcement?
Yeah.
Real quick,